Test obviously happened. I still have a couple more makeups. I do those during my office hours this week. So next week is when the office hours restart normally. This week, my office hours are makeups. However, so makeup should be done tomorrow, unless something crazy happens that I can't prepare for, can't explain. The test will be posted with all the answers on Thursday. So on Thursday, I'll actually post the test. You can see all the answers and the free response and all that kind of jazz. Till then, I won't really be able to talk too much about the exam, again, because there's people doing makeups, normal things. But yeah, we can talk about how, like, the performance and things like that. So just to quickly, there's a couple things I want to show. So, if you haven't seen already, there's the average is very good. Like, I'm very happy with this. Average is very good. There was a 4% curve added because the only so the way I do curves is I look at the answers and I see if there's questions that the vast majority of students are missing. And when I say vast majority, I'm talking like only like 30% of people are getting right kind of thing, 30, 35-ish%. That's kind of the level I'm looking at. If that's happening, what that generally means is I did not prepare you all well in some specific area. As much as I might feel like I've gone over that thing, if only 35% of people are getting it right, something is off. Something is off, and the only common denominator is me. So that's why I give a curve based on that. There was 3 questions. So I gave 4%, which is equal to one of the questions. I don't give all the points back. Yeah, so I kind of choose how much. In this case, it was 4%. 3 questions are off. I get 4% back, equivalent to 1 question. The free response, it is less likely that I do a curve on those because partial credit's kind of baked in there, and that partial credit kind of accommodates, gives me a bit more resolution, whereas the multiple choice, it's all or nothing. So it's pretty rare for me to do a curve on the free response. Grading the free response, just a reminder to you all, is the rubric. The rubric is super important. It was on the exam. And I think I posted it at some point. It's on the formula sheet, so that's where I'm scrolling through to find right now. So on the formula sheet is a rubric, and this is what we follow. But what I want to emphasize on this rubric, so it's everything that I've been telling you all to do. Did you draw a picture? Did you identify? And this is super important. Did you even identify what you're solving for? That sounds like an obvious thing to do. However, I actually don't see that. I don't see too often someone write like blank equals question mark or things like that. That's a really useful thing. Before you even start the problem, what letter am I solving for? What variable am I solving for? Is it C for capacitance? Is it Q for charge? Is it E for electric field? Is it V for potential difference or / voltage / electric potential? What is it? Energy, which is U. What am I solving for? Write down that letter. Why do I say that? If you know what letter you're solving for, it's immediately going to tell you what equations are going to be relevant to you. That's the reason this is super, super useful, super important. If you don't know what you're aiming for, you're not going to hit the target. Or if you're aiming at the wrong target, you're definitely going to get it wrong. So anywho, one of the most useful that's why you get basically 3 to 4 points just for identifying what you're doing and what you have. That's going to give you a good foundation. Now, if you then next part is, did you identify the relevant equations? And then the last bit is, did you use them appropriately? So I won't get into the details for this, but what I will tell you is if you identify the correct equation, the correct process, that automatically gets you around 50% of the points. Because if you've done so, you've identified what you're solving for. You've identified kind of what variables are in there. Ideally, again, the picture. Picture is always super good. It shows up in most problems. That lets me give you 1 or 2 extra points. So yeah, you'll get between 4 to 6 points depending on how much you've done in the previous steps if you just identified the right equation. Everything after that is, did you utilize it appropriately? Did you put all the bits and bobs in there appropriately? All that kind of thing. So that's also why I mentioned there's not a curve. Is this really emphasized if you have a sense of the process to do it, boom, you already got most of the points because that's what I care about. Given a problem, do you have an idea of how to proceed? Maybe you make some mistakes in the process, but you at least know the right direction to travel in. Anyway, so we'll get those graded. We're currently grading those. The way the free response works is so me and Angelina are grading them. We'll have those ideally done by the 9th, and then I'll have those grades in by the 10th, kind of at the latest. That's our time frame for pretty much all free responses. Make sure that we have time to go through them carefully. So it's kind of a balance of, I want to get the grades to you all, but I also want to make sure I'm taking my time and giving you the points where you deserve the points. So not just rushing through the grading. Okay. To that end, again, multiple choice, really, really happy with. If you have any questions, comments, concerns, you let me know. If there's anything that you're not sure what to do, all that jazz. Next thing I want to look at is a survey. So you all been responding to the survey, and we can look at the responses together. Don't worry, no one's names is going to pop up or anything like that. So it's all going to be anonymous. But I just want to show you other people's responses to these. I've already looked through them myself. This first question, I totally made a blunder. I meant to put, have you taken Physics 2 before? Obviously, all of you have taken physics before. You're in Physics 2. I realized that when I saw these responses. I was like, why did everyone put yes? Oh, I didn't specify which physics. The reason I say this is some of you might have taken Physics 2 in high school. There's like the AP Physics 2, but it doesn't count towards credit for this class, all that kind of jazz. Or maybe you've taken it before and you're retaking it. This is for me to kind of gauge. Obviously, if you've done it before, it's going to be easier. So this kind of gives me some of that information of what my population looks like with you all. Then the difficulty. I was a little surprised that the multiple choice was rated as high as it was difficulty-wise. That's fine, though. I'm not bothered by it being difficult. There's 2 questions, so this is just interesting information for me. There's 2 questions I'm going to point out that I really care about. One of them's kind of a given for this class, but we'll see when we do them. How would you rate the difficulty of the free response? You can see that these are shifted. The free response is the more complex, but that's where I give the partial credit and things like that, because I realize more complexity means more chances to make a mistake. All right. How would you rate the time? So this is one of those questions I really look at for this class. I assume you have more than the 2 hours and 50 minutes. I designed this test really for 2 hours for you all. So 2 hours and 50 minutes is, in my opinion, more than enough. So I'm not too worried there. In my lecture class, I really look at this a bit more because their time is much tighter. But anyhow, glad to see that most people agree. On a scale of 1 to 10, how much of the problem sets you go through? This is just kind of interesting to see how people are preparing. How much are people engaging with these things? That's just interesting information for me. How prepared did you feel? Also interesting for me. That gives a sense of this last question. This question is really important to me. How well aligned were the test questions to the teaching and resources provided? This is really important because this is something I have a big impact on. If I'm not giving you the resources necessary, I'm okay with giving you a hard test as long as I've given you the resources necessary to be able to do hard things. And so I'm glad to see that roughly does seem to be going well. So great. There's all that. If you have differing opinions, that's okay. The last one, I did look through this. I'm not going to open it because it's just a bunch of words and things like that. Largely, people, I think, were positive about things, but there was one big area I want to comment on. It's the request I get every semester, always. And I probably need to make mention of it beforehand because I always get this. The request is always more worked out solutions. I always get that request, and I totally understand why. And so the quick answer is, unfortunately, we're not going to get more worked out solutions, but there's a reason why. And there's actually 2 reasons I want to give you all. So we do work out things in class and all that kind of jazz. And of course, I'll work with you if you come to me or tutoring or whatever, all those things. The reason I don't give worked out solutions to every single problem is one of the most important skills I can teach you all. And I say teach you all. One of the most important skills that you can learn in your undergrad is what do you do when you don't have a worked out solution? Where do you find the information? What do you do when how to do the process isn't easily right there in front of you? So you're like, what? Why are you mentioning this? What are some cases? You all at some point are going to be solving problems that someone has not solved before. or at least not that exact specific problem. What do you do in that scenario? So this kind of gets down to, what do you do when you don't have the worked out solution? Where do you go to find that information? And there's a lot of options. You can go to me, you can go to other people, you can go to other quote unquote experts. Like, that is a viable option. Another one is learning to use Google and ChatGPT to find these things. It sounds maybe trivial, maybe it sounds like a cop-out, but anyone that's in computer science has learned by this point, how do you learn to code? You Google things. Like, that is every program. Computer science is just like one of the epitomes of this, because they have a vast amount of information online on this. One of the most important things you can learn to do as a programmer is Google. The same is true of every single one of your all's disciplines: engineering, physics. What do you do when you're confronted with a problem that you don't exactly know how to work out? And obviously, I provide my materials and resources. Googling used to be the answer, learning how to Google stuff well. Now we have ChatGPT, which basically is a synthesis of what's on the internet. And so in the next couple of weeks, I will make some activity for how to use ChatGPT within a physics context. So you can just take these problems, spit them in there, and about 95 to 98% of the time, what it's going to spit out is going to be really good and really accurate. Now, what if you say, but I solved it this way? Just ask ChatGPT, can this be solved this way instead? And if so, how? Or I solved it this way instead. Is that possible? The beautiful thing with ChatGPT versus Google is you can actually do follow-up questions. We've all gotten very good at Googling, where you put something in, you go to the first website, you read it. One of the new skills is having a conversation with the search engine. That's what ChatGPT you can think of it like that. Hey, how do you do? Why did you do that step? What would you do if this was different? Learning to ask those follow-up prompts. You have those questions, just ask them those questions. And to that, and another one is like, hey, this problem is really, like, you see the worked out solution. Hey, can you give me different versions of this? Can you give me modifications to this? Can you give me, I am in a physics 2 college class. My instructor is going to give me a test based on this. Can you generate a bunch of problems that might be different and variety? Like, be explicit in the context. The more context you give it, the better it can do. Just like if you were talking to a human being, treat it like you're talking to me. As weird as that sounds, think of the questions you would ask me and ask it, and it does a pretty darn good job. Anyway, we'll have a couple assignments on that. But learning how to do all that, that's one reason. That's the big reason why I don't provide worked out solutions, is I want you all to experience looking for information. I know it sounds like tedious and it sounds like a bunch of extra time and effort, but you're not going to learn that skill unless you have to. So this is kind of making you have to in some ways. The other reason is if there's always worked out solutions, you can sometimes get in this imposter area where, like, you look at it and you say, yep, that makes sense. You never actually try it yourself. A lot of people often end up studying that way. They just look at a bunch of worked out solutions, but they never actually hold a pencil in their hand. And I just don't want to. So that's a smaller reason. The bigger one is the one above it. So anywho, but at any point, if you all have problems or concerns with a question, you're encountering difficulties, please come see me, TALA. Email me. If you email me and you send me the work that you've done, I will also provide pointers. If you just say how to do this, that's going to be a bit too vague. I need at least something to go off of. I need to see some of your progress. Otherwise, I just end up having to solve the whole thing, and it's just not as useful. But if you say, hey, I'm at this point, I'm stumped, I can generally send me a picture of your work or something. I can generally very quickly point out what went wrong or what the next step might be. But you can also do the same with ChatGPT. You can literally plug in your work into it. It's pretty good at picking up pictures. I don't know how good it is at handwriting. That's maybe one downside of it. Yeah. All right. Less serious stuff. There's a joke.
I will say, before we jump into the joke, I do want to add that work with your peers. You work in lab groups, right? Like, it's pretty easy to ask the person sitting next to you, being like, hey, you want to, like, do practice problems together after class today? And it might work out. Like, I have a test on Thursday, and I still do this. Like, I sat with my friends this morning, and we did problems together. It really helps, because you learn, like, 4 different ways to do the same problem. All right, now, joke time. I have a chicken-proof lawn. It's impeccable.
It's good.
Thank you.
Yeah. So anyway, sorry for my big old softball. I know that was a long explanation to why I don't provide worked out solutions. That was very monologue-y, but I wanted to give the reason because I get that request all the time. And there is reasons. The reasons aren't, it'd be very easy for me to make worked out solutions. You know what I would do? Just stick every problem in ChatGPT and it spits out a worked out solution. So it's not like an effort thing on my end anymore. It used to be, but now ChatGPT can do it for me. So whatever. Fun fact, also the quality of ChatGPT is the point now where talking to one of the teachers who's teaching a graduate level physics course, he puts his tests into ChatGPT and he is seeing that it can do the graduate level course questions he's asking, and he made the questions. They're not like questions that he found online. So it's at the level where it can do graduate level physics work. So it can definitely do intro level work pretty darn good. It can also read pictures pretty well, like these circuit problems. You can put those in there, and it generally does a pretty good job, as long as you have good contrast. You know, white background, black font, all that kind of jazz. It's nuts. You know. Anyway, all right. So this week, so just to give you all a heads up, we have 5 weeks of content, and then we'll have our next test after that. So just like we had 5 weeks, then test. We have another 5 weeks, then test. It's going to be DC circuits, bunch of magnetism stuff, and then maybe at the tail end, maybe it says inductors, maybe AC circuits, maybe inductors. We'll kind of see what that time's used for exactly as we get closer. But this week we're going to finish up circuits. We've already talked about some of these things. In my opinion, this PowerPoint is going to be fairly straightforward. There's no crazy math. It's a lot of concepts in this PowerPoint. So we're going to have a lot of clicker questions in this PowerPoint because of that. It's going to be a good time. So we're going to talk about power. We already did, actually, but just to recap that, we've already covered it, so I'll go through it quickly. We're going to talk about 2 Kirchhoff laws, the junction rule and the loop rule. Kirchhoff is the guy that came up with them. Then we're going to use them. I will spare you the worst part about Kirchhoff's laws, which is solving them. You end up with a system of equations that takes a long time. We're just going to build the equations. You won't actually have to solve a system of equations. Then we're going to do resistors in series and parallel. That's going to be really easy. And then we'll talk about RC circuits, which, you can probably guess what that is. RC. R stands for resistor. C stands for capacitor. It's a circuit with capacitors and resistors. There you go. It's going to be a great time. All right, so ready to chat about this a bunch. I'm going to just kind of whip through this. We spent the time on it last time. What's the point of electricity? What's the point of circuits? It's to take electrical energy and do something with it. Do work with it. I.e. convert it from the energy it has to something actually useful. And we call the amount of energy that's converted per second the power. So it's du dt. How much power am I converting every second? I am not destroying power. I am not creating power. I am converting. I'm not creating energy or destroying energy. I am converting energy. You all might have seen this in your Physics 1 class as P equals W over T. Power equals work over time. If this varies, so W over T works if the work is a constant or like a total amount. But if it's changing over time, we do this derivative. And we're going to need that for the derivation. All right. I don't remember if I asked you this question, but we're going to find out. If I did, you should know it. If P equals du dt, what is power in terms of current and voltage? Hence, you're going to need the relationship between U, Q, and V. There's an equation that relates those. And you need to know that V is a constant. If you know those two, okay, there's one more thing. You need to know the relationship between I and charge. Between current and charge. But I'm going to let you all work on this for a bit, and then I'll sprinkle in some hints as it's open. Yeah. And that's the derivation. It's yeah. It's always nice when I can have them do the derivation. Yeah.
Or you can just think of it as V is potential energy per charge and I is charge per second. Multiply them, potential energy per second.
All right, so the first equation, U equals Q times V. Energy is your charge times your height, your voltage. Just like gravitation was mgh. Instead of N, you got Q, and mgh, you got V. And plug that in there and start trying things out. But you're going to want to be writing this out. Doing it in your head, not a good idea. And yes, the next slide does have what the P equals. But the whole point here is to understand where it comes from. Yeah, if you didn't realize that a lot of that works out way. But I want you all to discover it, not just like regurgitate something you saw. Yeah. It's just just your remember gravitation. If it was like the GH is the G, then the M is like the Q. How do you give something energy? And if it's gravity, it's the mass. How do you give something charge? Yeah, now next step is you're just putting where the U is, you just put that where the U is. And then we're taking the derivative of that, and I tell you something infamous that's going to make your life a little easier. So V is a constant. So what actually do is take your U and put it on U. And then take the derivative with respect to time. So the key here is put U where U is. Plug it on in and then take the derivative. All right, that's already giving you all a lot. This is the derivation. Give y'all 10 more seconds if you haven't figured it out at this point. But this is the derivation for it. It's really just it's one line. All right, in 5, 4, 3, 2, 1. The only thing you need I didn't give you is dq dt is a definition of current. It's how much charge flows through something in a certain amount of time. It's my flow. So that's I. So boom, P equals, the way I remember this is PIV. P equals IV. It's super easy. I don't know. It's a nice way to remember it. It's worked for me. I remember at high school someone said that and it stuck with me ever since. So stood the test of time. P equals IV. That's the equation for power. That's the derivation of it. Remember, everything in physics is not, we observe reality and then we use our equations and we plug them into other equations and we find cool things. So yeah, power, PIV, it's the amount of energy lost, and I don't know if lost or gained. Better way of phrasing this is the amount of energy changed by a device per second. The amount of energy changed from one form to another. So the unit is watts, and now we can start to connect it to reality. Light bulbs. Y'all buy a light bulb, it's going to be about a 14-watt light bulb. It's pretty standard for LEDs. It used to be 100 watts for incandescents. What do those mean? 100-watt light bulb means every second it's using. This is 100 watts is the exact same thing as 100 joules per second. Every second it's changing 100 joules of electrical energy into something else. And I have the utmost confidence in you. What is the electrical energy getting changed to in the case of a light bulb? You got this. Be confident. It's going from electrical energy to light. It's a light bulb. What's the whole point of it? It's to make light. Now, it's light and something else. Something else we actually don't want, but it's a byproduct. Thermal heat. Every time you all do an energy conversion, you're always going to generate some heat. You can sometimes harness it, other times not. In the case of your car, for example, your heater, when your car is able to use the thermal energy from your engine to heat up the air. So in the winter, if your car is cold, after you drive for a bit, the engine gets warm and it can utilize that byproduct heat. Sometimes you can do that, other times you can't. Why are LEDs more efficient? Incandescent light bulbs are 100 watts. New old light bulbs, they'll say like 100-watt equivalent, but they're like 14 watts. They are using, roughly, not 1/10, 1/8 the energy or so. Why? They're able to convert that energy more efficiently to light. As opposed to a lot of the energy getting lost as heat, in the case of an incandescent light bulb, LEDs are very efficient at converting it directly to light. So that's where the difference comes from. At the end of the day, anytime people design stuff, it's not so much about being able to produce more, it's just being able to produce what you want more. Whatever. P equals IV, very practical application of this equation for you all is if you buy a generator, and you're like, why is that useful? So back last fall, when the hurricanes were coming, I decided to buy a generator because I had a fridge and a freezer full of food. And my thought process is if I can save all the food in my freezer/fridge, that pays for the generator effectively. Hundreds of dollars of food, power goes out, all goes bad, unless you keep things cold. Why do I mention this? If you all buy a generator, let's just look some up real quick. All generators, basically what you're paying for mostly is how much power it can output. So if I just type generator, let's just see what pops up. Boom. There it is. This one produces 1,800 watts. Now, generally, these report 2 wattages. This one's kind of interesting that it doesn't report 2. Maybe another one will. And this is just fun facts for you all. This one just says 4,000. Great. Okay. It's in small print here, but it's very important print. It says 4,000 watts peak power and 3,200 watts running watts. What that means is this thing can produce 4,000 watts for a short period of time, but it cannot sustain that. It can sustain 3,200 watts. Why is there these two different numbers? When your refrigerator is not always running. Your refrigerator only turns on at periodic times, just like your air conditioner is not always running. So you actually only need this peak power for short periods of time when your major appliances are running. Otherwise, you can kind of get by in this standby. Anywho, why do I mention this? When I was choosing a generator, I needed to figure out the wattage of the appliances I wanted to run. If I'm trying to run 2,000 watts of appliances and I only have a 1,500 watt generator, that's lower. I can't produce enough energy per second. You can see the problem there. Now, here's the problem. When you all open your fridge door, there's a little sticker on the inside somewhere, either on the inside cabinet, on the door. It kind of varies. That sticker tells you the voltage and it tells you the current consumed. It does not tell you the power. How do you find the power? PIV. You multiply the current times the voltage and boom, you have the power requirement of your refrigerator. So it's actually very, very, that was one use case I actually ran into with this. And yeah, then you can look at other appliances to determine what you need for your stuff. So, very, very, very practical. On the bottom here, what I want to note is that there's 3 forms of this equation. Take V equals IR, plug it in, you can get the different forms. So I'll do one of them real quick. P equals IV. If I just replace V with I times R, you get one of the cases. So I times R, you get I squared R. Yay, you can do the other one yourself. Very easy substitutions. On the formula sheet, I only give you PIV, and I only give you V equals IR. If you want the other versions, make them yourself. Or write them on your note card. But they're pretty straightforward to generate. All right. We already did this problem, I believe. I'm pretty confident we solved this problem. So I'm not going to work it out. If you're like, what does he mean? If you all go back to the week 4 or week 5 PowerPoints, and we go to current and resistance, it's already like we did this problem at the very end. Boom, there it is. It's all worked out. So I'm going to leave that for you all. I kind of skipped these slides in between, but we did solve this problem. So if you want the solution to that one, it's in the last week's PowerPoint. I'm just not going to spend the time on it now because we already did it. All right, on to a plethora of clicker questions. We've already answered this one. See if y'all remember. How does a flow of water compare to the top paddle wheel to the bottom paddle wheel? Does the top wheel get more, less, or the same? And I'm asking about the flow. How does a flow rate compare? How does the amount of water that passes through per second compare from the top one to the bottom one? Is it more to the top one, less to the top one, or the same? See if y'all remember.
Those are well, I was thinking
All right, 10 more seconds. In 5, 4, it's really slow 5 countdown. 3, 2, 1. We're looking great here, y'all. You remember, good things. It's the same. Remember, if you're stuck behind a semi, how fast can you go? As fast as the semi. So, like, you're limited. There's only one path. Where are you going to go? You can't go around them. Everything has to flow through the same. Now, this next question, I need to change the wording. So this says, how does the flow of water compare? This is a different picture, and I'm going to change the wording first, and I'll come back. I put the word faster, which is not good because that results in confusion. So here I have a situation, and I'm asking about the flow of water through these two things. So in the last case, it was series. In this case, it's parallel. The one on the left is thinner, and the one on the right is wider. If I zoom in, you can see that, but I also put that in the problem so that you know, because it's easy to miss that. So how does the flow of water through the left wheel compare to the flow through the right wheel? Note that the left wheel is thinner than the right wheel. So do I get more flow in the left wheel? Do I get more flow in the right wheel? Or is it the same flow regardless of which one? So this is new. Yeah, and I changed it from faster to more. Faster would result in wrong answers. I care about how much flow. I don't care how fast they're moving. I care about how much per second. How much water per second.
Flow easier.
Yeah.
Okay.
Why not that?
Also gonna
Oh.
So if you want, we can make it
For the same course.
Yeah.
Yeah.
no, just to hang out.
Oh yeah.
Yeah. Yeah. All right. So to clarify, when I say thicker and thinner, this one's wider. This thing's wider than that one. This one's twice as wide as this one. So it's about the width. There's a height difference. Yay! I was like, you all know that's all. You all know this. There's a height difference. There's a height difference. And there's a height difference. All right, 10 more seconds. I think at this point, pretty much everyone has it. All right, in 5, 4, 3, 2, 1. All right, so the answer is going to be more flow. Pretty much what everyone put. But why? You got to think about why are they flowing in the first place? There's a height difference, but the height difference is the same. So it's just an advantage. Like you can think of it almost like then there's going to be a force due to it. But the right one has more room. Think of a 2-lane road versus a 1-lane road. It's way easier to get cars moving when there's more space. And so that's the thicker one. In this case, the one on the right. It's easier for them to flow through. So what I'm trying to point out with this is in series, current is the same. In parallel, voltage is the same, but current will be different if they're different things in it. Now, this is going to lead us to understand. We need to talk about current. We need to understand that current can be different in these paths. So this is we're going to introduce some terminology. Current is constant in a branch of a circuit. That's what you all decided right here. When there's one path, the current is the same everywhere in that path. So to give you a sense, like this up here is a branch, that top little segment, this middle part is a branch, and then this bottom part is a branch. They're all branches. When branches come together, you get a junction. Think of junctions like an intersection in a road. When you get to an intersection, you have a choice. You can go, for example, at this junction on the right. If I was coming into it, I have a choice. I could keep going straight, or I can make a right turn. We call it a junction. You got a choice. Now, just like when you're driving, if you want to get somewhere, you're going to take the road that lets you go the fastest. Why is it going to let you go the fastest? Maybe it's got more lanes to it. Maybe it's got less stoplights. It has less resistance. You're going to choose the path of least resistance. Some people are still going to choose the other path. That's fine. But that's the rule of thumb with current. It's going to go, and in this case, let's pretend like part of it goes up and part of it goes to the right. and it's going to split. Now, it's not going to split 50-50. It could. There's a possibility. If both options are the same, then it's going to be 50-50. But very often they're not. Very often one of them is more, quote unquote, resistive. One is harder to go through, one is easier to go through. How do we determine that? That's what we're going to learn today to determine kind of what paths. But all I'm emphasizing right now is that the current that goes in is going to split. And what goes in must come out. If 10 cars go into an intersection and 8 cars go through the top one, how many cars are going to go through the other one? 2. Otherwise, where the heck did my cars go? If 100 students come into this room, there's technically 2 doors. I don't care how you leave. However you leave, 100 students will end up leaving this room. Doesn't matter how it gets split up. It just matters that what goes in must come out. That's our first rule. Our first rule is called the junction rule because of junctions. What goes in must come out. If I add up all the currents going in, it will equal the sum of all the currents going out. This is a law. This is just how the world works. If it didn't equal it, then where did it go? If 100 students came into my room and only 90 students left, then there better be 10 students left behind. Otherwise, where'd they go? Current just can't. If it all stops, it all stops. So we're not going to stop. Yeah, things are going to keep flowing. And to clarify in this picture, I'll color code things. What defines in? It's arrows that point, and this is going to sound maybe stupid, arrows that point towards the junction, inwards, and arrows that point away from the junction, that's the out. In means towards, out means away from. It doesn't mean left or right or up or down. You can clearly see these arrows point in all different directions. But yeah, this is the idea. So we're going to do 2 questions based on this. One to get a sense of it. And both of these will reveal something kind of interesting. But yeah, it's a law. This is a rule. And it's one you've experienced your entire life. What goes in must come out. Otherwise, where'd it go? You know, you all eat food. That food's going somewhere. All right. Base image below. What's the value of I4? You got I2 pointed towards the junction. You got I1 pointed towards it. I2 pointed towards it. You got I7 or I3 pointed away and I4 pointed away. What is the value of I4? The current going through I4 in this picture. Yeah, that's easy. Yeah, just shoot me an email. You can email me now if you wanted to. All right. What do y'all think?
I think I will.
Yeah, there's no current and there's no current. Yeah. And this is actually a very normal thing to start. All right, 15 more seconds. All right, Tyler, you want to do this one? Sure. Depends what he'll say. All right, in 5, 4, 3, 2, 1.
All right. So real quick, just remember the law says that the sum of currents going in is equal to the sum of currents going out. If we have 2 currents, I1 and I2 going in, and there's 2 going out, it's I3 and I4. we can plug in these values. We know that I1 is 2 amps, I2 is 5 amps, I3 is 7 amps, and we don't know what I4 is just yet, but we can see that if there's 7 on the left and there's 7 on the right, sorry, this should be a plus, then I4 is just going to be 0.
And that's allowed. There's no rule that says because there's a wire you have to have current going through it. There's lots of reasons why you might not have current going through it. There could be a capacitor that got fully charged. When a capacitor gets fully charged, current will no longer be able to flow through it anymore. We'll learn that actually at the end of this. Another example of this is transistors. Transistors function that when current flows through it, it counts as a 1. When current's not flowing through it, it counts as a 0. Transistors are what your phone's made of, the processors. So anywho, great. Now, I got a really good question last class that I want to emphasize, that actually I'm going to use to make another problem. They said, what if they were all pointed inwards? What would happen then? Well, let's go ahead and do the problem. We're going to do the exact same problem, but I'm going to make every single arrow point inwards. And then, so I'm going to delete the answers. I'm not going to put answers here because it gives away a little bit too much if I put answers here. I will in a bit, but I'm going to let you think about it first. So what if instead I made all these arrows point inwards? We're going to solve that. And this is a really good exercise. And we'll see why in a second. Because these were arbitrary. Like, why are they pointed this way? I don't know. We just decided to make them this way. Let's see what happens when we point them all inwards. Again, I'm not going to send it, so spend 30 seconds thinking about this, and then I'll actually put some answers and send it to you. But if I start to put answers, it might give away too much. Do it the exact same way that you just did it. It's the same process. Find out what goes in, set it equal to what goes out, and then math. Try it. Yeah, I'll put it. That's actually the other way. And it's solutions for you. All right, so there's some answers: 0, 7, -7, and -14. Yeah, that's the whole point. When we're doing these problems, we're going to pick a direction for it, and if we happen to accidentally pick the wrong way, that's fine. The math will fix it for us. And we don't then have to go back and fix all the equations, plug in the negative, it'll flip the sign everywhere you want it. That's the same thing, you pick a negative, yeah. That's what math's so good. Yeah. All right, 10 more seconds. And 5, 4, 3, 2, 1. All right, same exact process. What goes in equals what goes out. It just so happens that everything goes in, though. So you get 2 plus 5 plus 7 plus I4 equals 0. And that means I4 is going to equal -14 amps, which everyone seemed to get. Great job. What's really cool about this is what does the negative mean? It means we just drew the direction of the current the wrong way. It fixes itself. The math fixes it for us. So this is going to be something we're going to do in these problems. Electrical engineers, we're going to learn about these Kirchhoff's laws, and you're going to have to suffer through them in future classes. Everyone else, maybe not so much. But when we do these problems, we have to pick a direction of current. But the great news is if we pick the wrong direction, it'll fix itself later on. You don't have to have the right answer when you start the problem. When we pick these directions, just pick some random directions, and if you pick the wrong way, you'll get a negative, and it fixes itself. It's great. Yeah, I've heard this a couple times. I guess statics, you have to suffer through the same thing. Yeah. So great. Just like that. It's a cool thing. And that applies to a lot of things. All right, so great. We talked about current. Current splits up when it runs into a junction. What about voltage? When does voltage change? When you go through a battery, when you go through a resistor, or when you go through a capacitor. There is more ways than this, but these are the only things we've learned about so far. Batteries, resistors, and capacitors all change your voltage. How much does a battery change it by? Whatever the voltage of the battery is. How much does a resistor change it by? V equals IR. How much does a capacitor change it by? C equals Q over V. Rearrange that. V equals Q over C. That's how much each one either will increase or decrease. Notice I haven't told you which one yet. We're going to have to do some extra steps to determine whether it's increasing or decreasing the voltage. There's going to be some process for that. Now, something very important that's not listed here and that we've mentioned before, but just to make it explicit, and I'm going to do this in all caps, junctions do not change the voltage. So when you hit a junction, your voltage stays the same. And the nice little picture for that, we've already done this. This picture here, there is a junction there. Does my height change? No. Voltage is like height. Just because your road splits doesn't mean that it suddenly drops off one of them. So voltage does not change when you hit a junction. Voltage does not change when you hit a junction. When does it change? When you either go through a resistor, a capacitor, or a battery. Does it go up or down? That's the next thing we have to practice. That's the next thing to learn. All right, so which way will current flow in the following circuit? So I got a battery here, a 12-volt battery, meaning my positive terminal is 12 bigger than my negative terminal. And then I got 3 resistors, and it's just a loop. What does this A, B, C, D mean? Absolutely nothing. They're just arbitrary points. They're just labeled for funsies. They mean nothing. On a circuit diagram, a corner like this means absolutely nothing because, you all can take any wire and bend it however you want. It doesn't change how it works. So, yeah, is my current going to flow clockwise, counterclockwise, or it's impossible to tell? And remember, current is the flow of positive charge. Which way would positive charge move through this circuit? Quote unquote. Positive charge move.
Yeah.
So the length of this wire yeah, we treat a wire like zero resistance.
It's just like a water flow analogy, right? It's going to go from higher to potential to lower.
Oh, I see.
Yeah, pretty sure. Well, I know because when the battery takes it from 0 up to 12 energy to complete the circuit. That's how that thing works. Did you learn the
the staircase or like the charge escalator or whatever they call it for the battery. Or like move charge up from like the 0 to the 5
I think that's what
Yeah, that's how we did things too. Probably a lot more sophisticated than I'm sure. The charge thing on escalator.
Now we just want to
All right, 10 seconds.
Right.
Again, think of it the way positive charges would move. That's what current is defined as, even though they're not actually the ones moving. Current is defined as positive charges moving, even though it's not the reality. All right, in 3, 2, 1. All right, lots of ways to think about this. But one of the ways, let's think of this voltage like a height. Voltage is like height. The 12 volts is a high voltage. The 0 volts is a low voltage. Positive charges are going to go downhill. Now, they're not going to go through the battery because that would defeat the whole point of the battery. They're going to go from this 12 volt and they're going to try to get to the 0 volts if we imagine positive charges flowing, and that's the direction of current. Now, notice that the answers aren't right, left, up, down. Why? Because if the current up here is to the right, over here it's going to be down. On the bottom, it's going to be to the left. And on the left side, it's going to be to the up. What's going to be really common in problems I give you is I'm just going to label current on one of these sides. So for example, I might just label the current on the top as to the right. If you know that, you know the direction of everywhere. Just follow the path it's going to take. This would be nonsense. Why is this nonsense? Because I got this is a one-way road. You can't go both ways. This doesn't make sense. So anyway, all that to say, clockwise, I think pretty much everyone's looking pretty good with that. Now, just remember in the back of your mind, negative charges are actually the thing moving and they're going to go the other way. You don't need to know that. I'm not going to quiz you on that, but it's just one of those. It's good to know the reality. All right, great. Current's going to flow this way. Nice little summary of that. Current's going to flow from high to low voltage. That's just the definition of like positive charge will move. Because remember, it's going to go that uphill to the downhill. Therefore, and I have a nice little picture on the next slide to help us understand this. Voltage drops. What's another word for drops? Decreases, goes down, lowers in value. Voltage goes down when you go across the resistor and you're going in the direction of current. So when you're going across a resistor, current goes from high to low voltage. That's a rule. We have that up there. So if you go across a resistor, my voltage is going to go down if I'm going in the direction of current. And my next slide has a nice little picture of like this voltage and how it changes throughout the circuit. To help us understand this, remember, think of voltage like height. Here, I'm at 12 volts. On the other side, I'm at 0. So as it goes through these resistors, I'm going to go from some height of 12 to a height of 0. We can see that in this nice little graph. We go through the battery. Think of a battery like a ski lift. The battery increases the voltage of the charges. It just increases the voltage. And then as you go down each resistor, in the direction of current, it's going to drop and drop and drop and drop. How much is it going to drop? I times R. Notice that these vary because these resistors have different values. What are they? I don't know. I didn't tell you. But bigger resistance, bigger drop. Smaller resistance, smaller drop. Nice little picture. And then it just repeats itself. If you just kind of kept going around and around and around and around and around. But this shows a nice little like height map of the voltage throughout the circuit. Now, I really like this question, and I'm not going to give any hints to any of it. What is the change in voltage in the circuit below? If I start at some point, I go around my circuit, and I end where I started. How much does my height change? If I start at some point, make a loop, and end where I start. Is my change in voltage 12, 6, 3, or 0? Pick any point on this circuit. I don't care where you pick. Pick any spot, start there, make a loop, go back to where you started, and find how much your voltage changed. The picture before this can be very useful.
There's 0 force, which is in some ranges. It's average velocity.
I was the board to read the whole question.
Well, it's your average velocity. The average force is even how you attack. So, like, crazy. If you
Every time I go around,
All right, give y'all 10 more seconds. Great. It looks like everyone's ending up at the same answer. All right, in 5, 4, 3, 2, 1. Now, this problem shows the power of collaboration. So the answer is going to be 0. I'll explain why in a second, but I just want to make a quick point before I explain why. My class this morning, and they are just as intelligent as you all. They, like 40 of them said A, 40 of them said B, and then I think like 80 said D. Why am I mentioning this? Why did this class get most of the right answer? It's not because you all on average are smarter than that class. We're law of large numbers. You all should be roughly equivalent average-wise. What's different? Collaboration. You all work together. Now, granted, we're also going around and helping you out. There's a bit of that guidance as well. But I don't think we talked to every person in this room. But you have the people where it just shows that when you work with other people, you make far less mistakes. And that's why anything significant in this world that's accomplished is done with a group of people nowadays. There's not really many people that are doing stuff on their own. If you look at someone and be like, wow, they're doing so much. They have a team underneath them that's doing a lot of work and stuff like that. Pick anyone and they have a team working with them. So anywho, just to make this point, the graph is the easiest way to make it. Pick literally any spot on this graph. I'm going to pick the spot here. Here the voltage is 6. How do I know that? Because if we go to the left, it says 6. If I make a loop and I go through this circuit, so go around. Well, I start at 6, I end at 6. 6 minus 6 is 0. If I start where I end, if you think of height, if I start here in this room, and then I walk around, and I go up and down a bunch of stairs, but I end up coming back here. How much did my height change? 0. You all have discovered the second Kirchhoff's law. The sum of voltages in any loop is 0. What is a loop? You start somewhere, and you end where you started. That's it. What is a loop? Pick somewhere, go with some loop in the circuit, go back to where you started, boom, you made a loop. And if you add up all the voltages, it's going to be 0. Why? If you end where you started, your change should be 0. Some places it goes up, some places it goes down, but they all cancel out so that you can end where you start. And this is the second law. And these two laws are kind of the foundation for almost any circuit. There's stuff online where you can build circuits and it'll like calculate the current through it, and it's just doing these two laws. There might be, if you got, at least if it's just batteries and resistors. If you got other things going on, it's got to use other things. But all right, now we got to figure out the voltage drops. So we've already talked about this. We need to understand whether we're going up or down. We've already kind of taught about this. So here's a little cheat sheet, and here the arrows actually look nice. Some other class they didn't. So the top is resistors. If I'm going in the direction of current, so remember, when we do this loop, we're going to be like walking this path. So I'm going to go in some direction. If I go across a resistor and my direction I'm moving in my loop is the same as the direction of current, my voltage is going to go down. Why? Because current goes from high voltage to low voltage. If you start high and you end low, you went down. So we get a negative voltage here. If you're going in the direction of current, your voltage goes down. That's just how current works. If you're going opposite the direction, then you're going to go up because it's the opposite. Current goes from high voltage to low voltage. So, if this is 12 and this is 0, then I went down 12. If this is 12 and this is 0, then I went up 12. There you go. That's resistors. Batteries is even easier. Batteries, we don't even care about current. Batteries, you just look at what side's positive and what side's negative. The positive side's bigger. The negative side's smaller. If I go from small to high, I went up. If I went from high to small, I went down. You just look at the battery. So in this case, the battery is 12 volts on one side, 0 on the other. So if I go from 0 to 12, I went up. If I go the other way, I went down. Batteries are really easy. You don't even care about the direction of current. Resistors, you do. Resistors, you do care about the direction of current. That's going to tell you whether your voltage goes up or down. All right, so now what we're going to do is we're going to practice building the second So you all practiced building the junction rule equation. Now we're going to practice doing the voltage equation. And with these two equations, by building a bunch of these, you can solve almost any circuit if you're willing to sit and do a bunch of math. All right, so here's the scenario. It's the same circuit we've been looking at. If you go clockwise, so you always have to pick the direction of your loop. You got to know which way you're moving. So if I go clockwise and the current's defined, you can see the direction of current. It's the way you all decided it was before. The current's also going to be clockwise. Build the equation for the total voltage drop. Sum up all your voltages. So remember the rule is the sum of all voltages. The sum of all of them equals 0. If I go up in voltage, it's a positive. If I go down, it's negative. But if you add them all up, you'll equal 0. Because I start and stop where I end. So go ahead and try to build it. Do note that this picture is very unfortunate. I don't know why. I missed this before. I don't even know how this happened. This is R1. This is R2. This is R3. You probably wouldn't have even noticed this. You probably would just assume this is to be true. That's what I did. But for reasons unknown, they're labeled weird. First resistor is R1, second resistor is R2. It doesn't really matter. It doesn't change anything in the problem. So great. Try it out. If you can do this, then you've learned how to do Kirchhoff's laws. And then after this, we're just going to practice them some more. But you'll never have to solve them in this class because it takes too long. might compromise.
We did all of them in my.
And you made them solve them?
Brutal. Yeah.
Yeah, so my compromise is I want them to know these laws.
Yeah.
I don't want them to spend
It's just algebra.
60% of the time
Yeah.
solving it. So basically, if I ask a question on a test or a quiz, it's just gonna be what's the right like.
What's the right side of it?
Yeah. Hey, here's draw a loop. I want you to draw a loop through these ones in this
Yeah.
way. What's the correct voltage?
Right.
I don't care if they can do algebra. I assume they can do algebra. All right. YD. Oh. YC.
Okay, I was like, wait.
YC.
Started with 12 volts.
Okay.
Since we're going in the direction.
Direction over, yeah. Why did the battery go up? Did you ever have one? So the other negative could go down. Why would the battery What's that do? If you're going, because which way, if we're going through the battery, we go this way.
But you can
So we're going
start
negative.
where the battery is, and then it's almost like right there, plus 12, and it has to equal 0 everything else.
I think it's losing, it's going down, increasing, trying to go faster.
You guys should think like it's
Negative going down.
Yeah, I got my head in So, if something really bad happens, I got that shit up there. They probably just didn't know they were. Like, I didn't know that we were supposed to scan your work. I think they just had the
All right, give y'all 10 more seconds. You want to do this one? All right, and 5, 4, 3, 2, 1. Boop.
There we go. All right, so for this one, we are going clockwise, and so I'm going to draw this big arrow around, and we see that our direction of travel is the same as the direction that the current is flowing in. And so if we look back at our picture, the direction of travel, direction of current is the same. You see that your voltage is negative, change in voltage. And so again, at R1, that's negative IR1. At 2, negative IR2. 3, negative IR3. And the last question is, what happens when we're jumping back up across the battery? Well, we're jumping back up, as I just said, so that's plus 12. And the answer is C.
Yay! Now, we chose this loop to be clockwise. What if it was instead counterclockwise? Because this is a choice you make when you do these loops. You have to decide to make it clockwise or counterclockwise. So what if instead you decided to do counterclockwise? Go for it. Current is still going clockwise. So there's two different directions here. There's the direction of current. The current's still going clockwise, but now the path that you're taking is counterclockwise. You're traveling through this thing the other direction. So to clarify that, last time we were traveling through it this way. Now we're going to travel through it the other way, the opposite direction. Build the equation for that. All right, 15 more seconds. All right, in 5, 4, 3, 2, 1. All right, so we changed our loop, which means now when we go across, and now we're traveling to the left, but my current's to the right. So I'm going up in voltage. Every time I go across a resistor, my voltage is going up because I'm going from, remember, current goes from high to low. So if I'm then going from low to high, I'm going up. So all that to say, all the negatives turn to positives, but now when I go across my battery, I'm going from high to low, so that's negative. All right, great. Now here's something that you might not have realized. C and D are the exact same equation. And you may look at those and be like, those aren't the same equation. How can I turn D into C? What can I multiply D by to turn it into C? Whatever you do to one side. So algebra says I can just take -1 and I can multiply it by both sides. You're like, what is he talking about? Unfortunately, I have to write out the whole thing. Algebra says it's the same equation as long as you multiply both sides by the same thing. If I multiply 0 by -1, it doesn't change anything. So all that to say, C and D are both the exact same equation. You plug in numbers, you're going to get the exact same answer. It's just a matter of, look, I can just take everything on the left and move it to the right, and now it's going to it's going to flip the sign too. Why do I say this? When you do these problems, the direction of the loop doesn't matter. You choose a direction, just pick something. It doesn't matter which one you pick. You get the same equation. C and D are... So technically, and I'll be kind, both of these answers are the same. It's the same exact thing. They're just whether or not you move it from one side to the other. You want to turn that C into D, just add all the terms to the other side. You're allowed to do that algebraically. So... great. No one picked C, but that's fine. And I'll even go back. And if you did pick D, it was the same answer. It doesn't matter. So the direction of your loop doesn't matter. All is to say, you pick a direction of current. If it's wrong, it'll fix itself. You pick a direction of the loop. Doesn't matter which direction you pick. It's the same equation one way or the other. It all works out. All right. So here they are together. And we'll take a break and then we'll practice these. This is just a summary. And then we're going to... practice it on a problem, but I'm going to spare you the algebra. That's my gift to y'all.
For fun, I guess. Yeah. For torture. Evil.
You don't like that? You can think the other way. I tell them, so like on the quiz problem, so I made a quiz problem for this, I do the same thing, and it's just so that there's one right answer. There's one specific answer I'm looking for to make sure you are going in the right direction.
Just to like normalize it.
Yeah. I want to test if you know that you're going from this to this, it goes down, or this to this, it goes up. This is my, okay, it's been a decent amount of time, so like, I want them to learn Kirchhoff's laws. I don't want them to do this system equations. So it's just build the equations. If you can build the equations.
I wish I had you for this, but
it's just, the algebra is a waste of time.
it took us days.
Yeah.
And then you can't like make the problem as interesting.
Yeah.
Right.
You just spend all your time doing algebra.
If you make one mistake, you've got like a whole page
Yeah,
that's
it's
separated into like equations and stuff.
Yep.
And
No, I don't
it does not drop the point home
I
at all.
don't want a mistake to be algebra. I want it to be. And even like when we were doing courses,
Mhm.
yeah, they don't care about the algebra mistakes. They care about do you know the process. It was a factor. It was a running joke of where that factor two came from. Whenever we were in grad classes, and we were solving problems, it was always mine's off by a factor two. Or where'd that negative sign come from? Where'd that factor two come from?
Like how this one right now, like I can ask if you want now to be
Oh yeah.
just like flipping no, they're not asking that.
Yeah.
Because like he wrote the whole thing in his like design list, and he was like, well, your efficiency is they're not right. Like and then we just took that
Well,
little
I ran into that with, so I did resolve it. So that whole voltage being negative. So the reason it's negative, so we have the E equals negative E dot dl, or let's put it dr. So the electric field equation for a point charge is So
You're saying
this
it's
is
all right.
always positive. Yeah,
Yeah.
so this is going to be positive. And this dr is also always positive. The definition of dr is always, what is dr?
Right.
It's always outward,
Yeah.
always. Like, so this dr isn't
It's
actually.
DR or hat, right?
Yeah.
Pretty much.
Yeah, so all that to say, this always ends up being positive.
Yeah.
Based on the unless this one's negative, unless you had a negative charge, in which case you would put a negative sign. Then the direction to travel comes from your bounds.
Yeah.
So I was double counting the direction to travel when I was doing the dot product. So yeah, it comes from the mathematical, like you just think of this in variable form. This is positive. This is positive. Yeah, the Griffiths was doing, or no, one of my previous students, so Robin, who may have been interacting with her, and she sent me something from her textbook. Yeah,
Hey, kind of fun.
Yeah.
I don't know what it is. It just seems so wrong.
So I didn't realize that I wasn't able to. So I was trying to find force on the correct carry. So if I do a loop, so the two problems, ironically, it's just like Coulomb's law. So I'm gonna have like a loop of wire with some and like a magnetic field.
Yeah.
And we want to find the force on this. So F equals I L cross 2. The direction of my I or my L changes. So what we're going to do is dF equals I dL. And you're going to integrate to get the actual force.
Yeah.
So in this case, it's going to be the angle will change. The force. Well, so you have to do the cross. Now, it's always, in this scenario, they all add. So you do have to realize that this force is out of the page, this force is out of the page, this force is out of the page. So anywho, they'll, and it's really simple. It's RD theta, sine of theta does just match. So that's one.
Is that one where it's just angular? Like, you know, it's just the angle changing for that equation?
Yeah, and in this case, the sine of theta is the angle between this and this is changing. But the forces, I don't actually, they're all pointed this way.
Oh, okay.
So I don't actually do an X and Y component of that.
Yeah.
Another one I can do though is my D is into the page.
Oh, right.
And in that case, this would be a constant, but we will break things into X and Y. Because the forces here will be over here, the force will be this way. Over here, the force is this way. So ironically, we just multiply by sine of theta. We still do.
Right.
It ends up becoming the same thing. So this is one type. Another is just a straight wire where I have a magnetic field.
Not the double.
So it's similar idea of building the integrals. Write this, write DL, change DL, DL here, just DX. So it's gonna lean. Thankfully, it is gonna lean on the same skills. Hopefully,
Just different contracts.
yeah, just different. And it's just like it's an infinite sum. That's really what I'm gonna emphasize. If you have something that varies, an integral doesn't. So yeah, I realized that when I was setting up problems, I was like, oh.
I never really kind of thought about it until somebody pointed out that the integral sign is just S. It's like the summation, like sigma, but it's continuous.
Yeah.
So,
Yeah.
not discrete.
All right, y'all. So let's resume. So this is the summary. So how are we going to use this? So this is the recipe. And this is something I'm going to try to keep doing moving forward. Anytime there's a problem that has multiple steps, you saw it with Coulomb's law. I made a nice slide on the recipe. Gauss's law, recipe. There is recipes to these problems. There is a process. Just like when y'all do force problems. Draw a free body diagram, sum of forces equals ma, and the x, yada yada. So great. What are we going to do? We're going to label and show the direction of current. How are we going to decide this? I'll either tell you or you make it up yourself. You get to make it up if you want to. Remember, if you pick the quote-unquote incorrect direction, that's okay. The math will fix it for you in the future. Now we're going to draw loops. These loops are the direction I'm going to travel. These loops are not the direction of current. They're the direction that I'm going to travel through my circuit to sum up the voltages. We're then going to build the voltage equations. We're going to build the current equations. What do I mean by the current equations? The junction rule. What do I mean by the voltage equation? The loop rule. Then, and this is the one I'm going to spare you on, use the system of equations to solve for the desired current. I'm not actually going to have you do that on tests because it takes way too long. Those of you in statics classes are getting lots of practice with this. Rule of thumb in this class, the math should only take you 20 to 30% of the time. 70 to 80% of your time should be setting up the equations. Only 20 to 30% should be the math. These problems, if you're solving the system of equations, most of your time is doing the math. And so I'm not going to waste the time on that. It's not worth it. You all have lots of algebra practice. So you're spared that suffering. But we're still going to build the equations. Then we could say we could solve this if we really, really wanted to. Right? And as I mentioned down here, you don't need to pick, quote unquote, the right loops or direction of current. It all works out one way or the other. So let's practice. Here is a circuit. It says build the 3 loop equations and 1 junction equation. You could actually build 2 junction equations if you want, but they'll just be opposites in this case. I tell you the direction of currents just so we all get the same answer. In this one I say make I1, the current 1, pass down through the 50 ohm resistor. Make I2 pass the right through the 12 volt battery. And make I3 pass right through the 100 ohm resistor. Are those the right directions? I just made them up. But it was just so we get consistent answers. More often in these problems, they don't tell you the direction of current. They just say do it, and that's fine. There's nothing wrong with that. I just did this so we all get the same answer. Because we're building the equations, and I'm not so much worried about the answer. Now, I did say we're going to find the current. That's because this specific problem, you don't actually have to solve the system of equations. You'll see when you build them. So try it out. Oh, and I said there's 3 loops. This is one of those puzzles. How many loops are there in the picture? There's 3 possible loops here. See if you can figure them out. It's like one of those puzzles. How many triangles are there in this picture? So see, make sure you can draw all 3 loops. If not, call one of us over. We'll help you out. Or ask the person next to you. They'll help you out.
That makes sense.
And whenever you draw these loops, you should never go backwards. You only pass through each circuit element one time. If you go backwards, you're just going to cancel it out.
And my sign could be wrong.
If you minus the I1 here, right?
If you want to check the answer to the problem set.
Because we're going
Yeah,
with the directions, and then if I went here, we're going again. Yeah.
How is correct?
It's going this way. wrong direction.
Would it not go? It would be pushed by the bigger voltage, right?
No. So like in this top loop here, you would subtract this voltage drop. And
Yep.
then would we
Yeah,
subtract this as well?
Yep, because you're going from the high to low.
And then we go back up here, we're adding 5.
Just because you're going from high to low.
Yeah.
Yep.
Okay. So then, you know if these are right?
No, I have no clue.
Okay.
This one doesn't require a system of equations.
Yeah, I noticed that after I said it. I'm like, oh wait, I can just solve.
I purposely made this one nice.
Yeah,
The
that's-
next one's not nice.
Oh, good.
But I'm not going to make you question it. It's in the problem set that looks pretty right.
Maybe there's like a decimal.
It might just be right. I don't know. My memory's terrible.
Problem set 2, right?
Yeah.
Oh, I see. Yeah. It is a decimal. Yeah.
So your third loop
That's
is
gonna be
the
the
outer
first step.
stuff.
The whole,
Yeah.
everything but the middle. Yeah. Okay, yeah, it was right.
Yeah, you can do
Cool.
like that. That's
Yeah, you choose decimal.
for the currency. That's more than fine.
So, yeah, I'm so worried about the sign for the middle, the 12 volt battery.
If you would instead decided, so
I think we have this one.
12 minus 1 battery.
because the direction matters. So if instead you decided to make the currency,
Because yeah, I guess so for batteries it does not matter the direction of current, right? It's just matters which end you enter that low to high or high to low.
Yep, and then do the same on the other branches, just like you did. The only thing on yours, they're gonna want to be labeled because when you're building the equations.
I don't know.
It's a good question. I mentioned the long side of the battery is positive, the short side is negative. That's the notation there. Long side is positive, short side is negative. That's common notation for batteries.
You understand what like the equations would be?
But what I'm going to be looking for is, did you draw the currents? That's the first step. Draw this and draw the currents in the direction they're moving. Draw your loops. Remember, those are if you go back to the recipe I gave you, that is the recipe. This is how you do these. Draw the directions of current. Draw the loops. The loops and the direction of current are two different things. Current is current. Loops is like, imagine you're walking this path. You may or may not be walking in the same direction as current.
And then the junctions, law is I1 goes in the junctions, and then I2 and I3.
Yeah, the direction.
So then I1 must be.
Are these the right directions?
Remember the junction.
They are actually
Yeah,
the right directions.
I know it's a lot. A lot of ones. Yeah. You got
The
that.
reason is that these will be the right because these are lined up this way. When you draw these, make sure you draw one in bigger. The reason I say that, that's your positive terminal. That's your higher voltage side. That'll be important. Yeah, the current's gonna But again, it doesn't actually matter if you know which way to go. You just pick a direction. All right, so to draw those arrows on here, so it says that I1 passes down through this. So I1 passes down through the 51. I2 passes to the right through this one, and I3 passes to the right through that one. Is that actually correct? Is that actually the direction of current? Who knows? Doesn't matter. If it was the wrong direction, the math would end up fixing it. And in this case, we'll actually find that the current I2, if you found it, it's not going to be that way. But it doesn't matter. That's the whole point of this. It doesn't matter. I just picked directions for you all so that we all get the same equations. If you did it a different way, you would just have different plus and minus signs in different areas. The last thing is you draw some loops. There's 3 loops. Again, basically the question is how many rectangles can you find? A loop is kind of like, it doesn't have to even be a rectangle. I can start here, boom, that's one loop on top. That's one loop. There's another loop down here at the bottom, and then there's a big loop throughout the whole big thing. These loops are just a path I can take to go from one place to the beginning without crossing over somewhere I've already been. When we're drawing these loops, we're just drawing something such that I start somewhere, I take a nice little journey, and I end back where I started without having gone over somewhere I've already been. Anyway, so now build the equations. This is just a checkpoint. So if you can't get this, you won't be able to start building the equations. You want your resistance on there.
You have to do that at one of the junctions.
And your batteries, you're going to log in and short in, so you know which end is the high voltage. Would you get your equations? Because when we're going through, we go this way, that's going to be high. Whereas if we don't, but you won't be able to figure out what's high.
Oh yeah, you gotta say R1. Yeah. What is subtraction? Because if you're basically reversing the current improvement,
just draw. If you're wrong, it's okay. Because you just did the math.
So
In this case,
And you know the volume for that.
Just take your best guess. If your best guess is wrong, we do the math to set out a negative. You can be like, oh, okay, it's the other way. Yeah. It'll tell you what. The thing is, they don't solve. This one we will solve.
Yeah.
I just go through the battery, right?
Solve is when you build the equations. Other ones are potential button solves, and so we're going to avoid that. They're not hard. They're zero.
For the first,
And then already you can solve for the current, right?
for the first move,
And
I would R1.
Because we have three currents. And
Yeah,
so we need multiple equations for multiple unknowns. Yeah, so this one actually, you technically won't need multiple equations to solve multiple unknowns, but other versions of these you do. It's really common for these that you do this to have all the equations to solve them.
yeah, there's no like numerical one there.
And you can do so like this one you're gonna see. So for example, when you do this loop, there's actually only one unknown. We know the voltages of these, we just don't know this current. This one you have two unknowns, but actually we don't need to use this current. You did the big loop here, it looks like. Yeah, you did the big loop. That one needs to be two unknowns, so I can't solve that one. The other loops end up being immediate. How would I make one where multiple? If I had resistor on this one as well, then we would need all these equations. Just like when you built this one, you had two currents. If there's multiple resistors in your, if there's multiple currents in your loop, you need multiple equations. All right, you can actually solve these. These ones you can solve. They're, without having to do assistant. Like it's, I picked the easy one for you all to actually solve. Something you don't have to do, but it can be maybe useful, is to like color code these loops. If you have the ability to do that, it can be nice. Otherwise, I guess you'd call it like loop 1, loop 2, loop 3. I'm going to do that just to keep track. So I'm going to start building them. All right, so we're going to do the purple loop first because that's what my pin's on. So my purple loop, I pick somewhere in the circuit. And remember, think of this loop like the path we're taking. We're walking along this circuit. I'm walking. I hit the resistor. Does my voltage go up or down when I hit this resistor? It's going to go down. Why? How do we know it's down? When I go across this resistor, am I going in the direction of current or opposite the direction of current? Direction of current. Current goes from high to low, always. So when I hit this first resistor down here, I am going to go down. How much am I going to go down by? IR. I3 times 100. Why is it I3? Because that's the current that's in that branch. Cool. I'm walking. I'm going around the circuit. Nothing happens. Great. I hit the battery. Should my voltage go up or down if I'm going from the small end to the big end? Up. The big end is positive. The small end is negative. So I go up by 12. And I end back where I started. Boom. Loop done. First equation done. Do the other three. Do the other two if you haven't done them. And then solve for the currents. So there's two more voltage ones. Well, let's just do the current one real quick. Pick a junction. Which junction do you all want to do? Left junction or right junction? Left junction it is. Looking at my junctions, I have I1 pointed in. I have I2. Is that in or out? Is it pointed towards the dot or away from it? Away from it. I2 is pointed away from this dot that I'm looking at here. What about I3? And if you look at I3, you're like, but it's down here. Well, it's also right here. So my junction rule here says that I1 equals I2 plus I3. What goes in must go out. I1 points in. I2 and I3 point out. Boom, there's the one. If you all chose the other junction, you'll get I2 plus I3 equals I1. It's the same equation. If you all pick this junction over here, which way does I1 point? Up. Which way does I3 point? In. Which way does I2 point? In. So, pick your favorite. They're the exact same equation. So the key here is realizing that current kind of wraps around these branches. Just imagine this flow. Anyway, build the next two equations, try it out, solve the things. Call us over if you're stumped. Call us over if you're like, I don't know what I'm doing here. There's steps involved. This is a complex problem. There's a bunch of steps. Complexity is literally just a bunch of steps in a row.
We're just worried about the pressure. That's all. Yeah, override.
Well, the problem is I mean, yeah, you can guess the quiz to get 3% here. No. 18%. 3. Oh, yeah. I ever did it in 7 parts. He was just 3 months, and it was for
Yes. Yep. I kind of almost feel like that, I guess. How goes it over here? Y'all feel some pretty equations? Let's see them. All right. Cool. Okay, show me a loop and then we'll picture the equation. Take a loop, any loop.
Yeah, I think my first system.
Cool. Alright, think somewhere to start. We're gonna start walking through the circle. Great. We haven't gone through the element yet. So we're gonna start here, and then we're gonna start walking. We're not actually gonna say what the voltage is. We don't say what the voltage. We start going through the circuit. We're adding up. Because we're not sounds. That might not.
So we still need
Yeah, for example, this is here.
No,
So we don't actually know when the voltage drops or up and down. It's that way. Water here, we
it is. Well, I don't remember learning trust. I learned trust.
We don't actually know.
We didn't know it was in church. I might be wrong.
It's an arbitrary. We pick this direction. This direction we just got wrong. If this
Principles of
approach goes high,
I think it is just a continuous
we're gonna go.
So
If we're traveling this direction, we're traveling down.
Yeah, it's just
I'm the same way. Yeah. I mean, I'm just
It's not like he gives like these lockdown practices.
So big end is the high end, and small end is the low.
yeah.
I would not recommend.
Yep. Might as well. Walk. If we hit this battery, and are we walking from the low to high or high to low? So that's gonna be. There you go. All right. The key here, y'all, and I'm gonna make this really big. This is very much, do you understand what you're so we have all these things, we have our currents labeled. I'm going to draw them again real quick. This problem is a very process problem. Do you know the process? And so, I3, and then we got our loop in here, we got our loop in here. These are not, like there's a bunch of steps to these problems. All right. I think we did, which loop did we do? The top or the bottom?
Bottom.
We did the bottom. Let's do the top one. Here is the conceptual way to think about what's going here. Pick somewhere on your circuit. I'm just going to pick this random dot here. I don't care where you pick on that loop. Pick somewhere. Imagine you are there. Imagine you're there, and we're going to start walking through this loop. Imagine you're physically traveling through this loop. So we're going to start walking. Which way do we walk? What's the direction of our loop? Counterclockwise or clockwise? Counterclockwise. So we're going to start walking counterclockwise. We walk. Nothing happens until we hit that battery. We hit that battery. Are we going to be walking uphill or downhill when we go across that battery? Uphill. We start at the negative terminal. That's the bottom. Positive terminal is the positive. So we go uphill. How much do we go uphill? 5. We go uphill positive 5. Great. I made it through the battery. I walk. I hit this resistor. Now, when I hit this resistor, my question to you all, I'm going to go through the resistor. Am I walking uphill or downhill? And the way you figure this out is current. Which way does current flow? Does current flow uphill or does current flow downhill? Downhill. So if I'm going in the direction current's going, am I going downhill or uphill? Downhill. So how much is my voltage changing? Take your current and multiply it by your resistance. That's how much down. I'm going downhill because I'm going in the direction of current. Current flows downhill. And that's how much. Great. I walk through my resistor. Walk. Great. I hit this battery. Again, I'm just following this loop. I'm walking through it. I hit this battery. When I go across, am I going uphill or downhill? Downhill. How much am I going downhill? I'm walking. Boom, I'm back where I started. I'm done. That all equals 0. This might sound stupid, but if you can imagine this process of kind of walking uphill and downhill, that's how you build these equations. And then all you need to know is that current flows downhill. If I go opposite of current, then I'm going to be walking up against the stream. I'm going to walk uphill. So great. That's the last one. One more equation that we didn't do, and I'll just spit it out real quick. We got the big loop. If we did the big loop, we're going to get that positive 5. We're going to get that negative I times R, which this R is 50. I'll just put that value here. We're going to walk. We're going to hit this one. We're going to go downhill again not because I'm going across a resistor, but because I'm going in the direction of current. And then we walk, and we end up back where we started. That's the second equation. And then the third one we built before. So that was this one down here, which was 12 minus I3 times 100 equals 0. These are problems you're going to have to practice. There's another example of this in the problem set, and there's an example of this on the quiz. This is a skill that's important. There is enough steps here. Very easy free response question. What problems do I put on the free response? Problems that involve a process. Problems that aren't just, hey, here's an equation, plug in numbers and hit go. Build the equations. That's a really common situation with these free responses. Build the equation. So, anyway. So that's that. If you have any more quick questions, I can run around. As far as solving it, these are actually quite easy. You're spared. Normally these ones, all your equations often look like this middle one with 2 unknowns, and you got to do a system of equations. I1 and I3 are pretty easy to solve here. If you haven't solved them, I'll give you all 5 more minutes to do so, but I'm going to put the answers up here. You got a bunch of equations, solve them. We find that I1 is negative 57 over 50. We find that I3 is 100 over, or 12 over 100. The fact that our I1 is negative, what does that mean about the direction of I1? It's going the other direction. Does that mean we made a mistake? Not really. Like, I guess technically you can say but it doesn't matter. It fixes itself for us. The math revealed all. So it's fine. It's like when you are doing free body diagrams of forces, you get the acceleration from doing the math. It works out. If you get a negative, great. It's just the other direction. That's fine. Nothing wrong with that. Ain't gonna hurt you. But yeah, give you all a few moments to try these out, solve them. So the key here is walking all these paths. So which loop are we doing?
Yeah.
It doesn't matter.
That's pretty much separates the really fast and like eco-plastic
No, you can only take the day of. The day of.
They do a little bit of office up there. Yeah, I remember we did.
I think we just until we get to it.
Yeah, we do optics at the other stuff, like a little bit, dependent, time dependent. Yeah.
I think we will. So just look, I didn't actually. We have a week more than I thought. I thought we only had 4 weeks before the next test. But we actually have 5.
Oh.
So that means we're gonna get through like everything that you field lines and maybe VLM and touch on AC circuits.
I think we did AC in mind before the second term, but just
It's gonna be very like brief. It's gonna be inductance, phaser. I'll use the phasor diagram just to show why, but and yeah, so we should be able to get to optics. At least a week, if not 2. Now the challenge is if we just get a week, I'm only going to be able to do Snell's. What is light? Snell's law. Yeah, light is both the thing. Speed of light stuff.
Snell's law is just what, like the angle of the fracture being equal.
If we then have more time, we'll then do Lindsay's slash. We'll do one or the other. Because honestly, if you do one of them,
it mixes up.
One is enough. One is enough.
Definitely don't.
All right. Okay. So great. So there's all that. We're not going to spend too much more time because again, we're doing decent on time. But I do want to just kind of quickly run through. We'll do resistors in series, and then we'll see where we're at after that. I don't want to make any commitments. All right. You're going to have 2 setups: series and parallel. Hopefully, these aren't new words. In series, current is constant. In parallel, voltage is constant. Why? We spent a bunch of time talking about that already. Remember, they get the same height in parallel. That's the definition of parallel. Cool. All right. Resistors in series. Already just put the whole derivation. Okay, great. You all built this equation. If you're like, what's going on here? You all built this equation. It's one of the clicker questions. It's this circuit right here. Current's the same in series. Factor it out. Oh, look. What do the resistors do? They just add. If you factor out the I, what we can do is we can turn these 3 resistors into 1 resistor. And you can just see that from the equation that you all already derived this equation. All I did was pull out the I. And by pulling out the I see that all these resistors just add together to get you a net resistance. So boom, there's the derivation. How do you add resistors in series? You just add them. It's great. It's the opposite rule as capacitors. Capacitors in series was the inverse. And rule of thumb, if you're adding numbers, you always get a bigger number. Always. I don't care what number you add as. There's no negative resistances. There is no such thing as a negative resistance. That's an important point to make. You can have 0 resistance, but that's the smallest you can get. That's what a superconductor is. A superconductor, what is it? It's a really good conductor. What makes it so good? It's got 0 resistance. That's why it's super. But they're what MRIs use and all that jazz. We're not going to get into the mechanisms and how they work because people don't know the mechanisms and how they work. It's not like, if you take enough classes, you'll eventually learn. No, it's one of the great mysteries out there. We don't actually know how superconductors work. But it's a work in progress. If someone can figure it out, the holy grail is a room temperature superconductor. We'll all have flying cars. It'll be great. All right. Great. So you all already built, to derive this, you had to build the voltage thing. We just did it. Great. You already did it before. Awesome. Go ahead and build the junction rule for the following circuit. I have some current going through it some total current, and it splits up into I1, I2, I3, I4. Build the junction rule. What goes in must come out. Yep. Yeah, so we're just going to finish up this in the next few slides. We'll actually leave the practice problem for next class. Because we're doing pretty good time-wise.
C is just B.
But actually,
This is going back to the jump
Yeah, it's you think it's 50-50, but it's actually
I was like,
you are right. You're also
I got
There's three options. You can take one away.
There's just so many.
okay. So I'm gonna think there's a car behind one, there's two goats behind another. Pick one.
Yeah. So this is actually
Okay. Now I'm gonna say there's a goat this way. There's a goat there. You can just swap and pick one. Okay, so listen. So let's say the car was this, right? That means it doesn't matter what you think. Oh, okay, I got it. So if the car is not in this, and let's say the car is in this, both of these are go. It doesn't matter what he eliminates. So if he eliminates two, because he has to eliminate two, there's 2 in 3. Because these are the 2 boxes. If you pick up, yeah.
easier to think about what
It's not an equal change. You have a 66%. We're going to run this 3 times. And we're going to see how many times you get it right.
All right, 10 seconds. All right, in 5, 4, 3, 2, 1. All right, so I did something purposeful here. Everyone got the right answer, so that's really good. Both B and C are right. How do you know that? Algebra. If you just move all this stuff to the other side, it becomes a negative. That's fine. Why did I write it both ways? One of the reasons, I don't even know if I had this intention, but I'm going to take advantage of it. If you all go to the Wikipedia page for Kirchhoff's laws in your free time, just for funsies, you're really excited, so you type in all caps. Kirchhoff's laws. They write the current law different. They just write sum of currents equals 0. Now, why do they do that? What they do there is they just say in is positive, out is negative. You can do that, and you get the same exact result we did. So the way I taught you all stuff is I put the sum of current in. So I wrote it like this, I in, sum of currents in equals sum of currents out. The way they write it is they just sum the currents, but they define in as they pick a direction. It doesn't actually matter. Let's define in as positive, out as negative. You get the same answer. So in this case, we decided to do this. So I decided to make in as positive. So the I net's coming in, so that's positive. And then the rest of it is going out, so it's negative. Mathematically, it's the same thing. I just did this some in, some out. It's a little easier to understand. But they're both the exact same thing. Exact same thing. So, boom. So which one's right? Both. Doesn't matter. Pick your favorite. All right. So what are we gonna do with this? Last little derivation for y'all. In parallel, you all just told me that they add up, right? We're cool with that? In parallel, in V equals IR. So just plug everywhere instead of I equals V over R. So focus on this. Just put that into each of these. Everywhere there's an I, put a V over R, V over R, V over R, V over R. But they all have the same V. So take this V over R, chuck it in each of these. Yay. If they all have the same V, what happens to all the V's? Boom, they're all gone and they get replaced with ones. How do you add resistors in parallel? The reciprocals. Why? Because of these rules. In parallel, voltage is the same. In parallel, the currents add up to get the total current. Yay. So long story, there's a nice little, so basically we can take this one circuit, just like we did with capacitors. You can take a bunch of them and turn it into one of them. And this is that R net. What is my voltage drop across R net? The exact same voltage drop across all these resistors. And so we're not going to do this today. We're going to call it pretty much good here. Next class, we're going to practice it. We're going to do this circuit. We're going to combine them together. And so the big punchline, just kind of put all the pieces together, is you all have two different ways to kind of do these circuit things. If you can do them all series and all parallel, you can do that. If not, you have to do Kirchhoff's laws. If you all go back to this, if I have more than one battery in a circuit, you're going to do Kirchhoff's laws. You do not get a choice. If it's just one battery and a bunch of resistors, then we can just combine them into one resistor. But we couldn't do that for this problem. That's why we had to go through this more complex system. Anywho. Great. Have a good one, y'all. I'll stick around if you have any questions, comments, concerns. We just got this left in RC circuits, and then we'll have a lab on Thursday, and we'll start talking about magnetic forces. And there will be integrals. More to prepare mentally.
What's the lab going to be?